Hello and welcome to Armagh Astrobytes. My name is Michael Burton. I'm the director of the Armagh Observatory and Planetarium, and Astrobytes is where we try and tell you about the cosmos in bite-sized chunks. Well, today's first Astrobyte is about astronomy and the birth of science. I'm going to very briefly tell you how we went from a geocentric view of the cosmos, where everything moved around the Earth, to a heliocentric view of the cosmos, where everything moved around the sun. We're going to go from the story of the philosophers from ancient Greece to the scientists of the Renaissance. So let's very quickly go through some of the great works of the ancient Greeks. And indeed, there were great works. Pythagoras, around about 500 BC, thought that natural phenomena could be described by mathematics. We've all heard of Pythagoras' theorem for a triangle. Music of the spheres. Aristotle studied motions in the sky. He deduced the Earth was spherical. He explained the phases of the moon. He thought the universe was governed by physical laws. Aristarchus, about 300 BC, worked out the scale of the solar system. Indeed, he even postulated the concept of a heliocentric model with the sun being at the center. Unfortunately, this idea was later lost. Eratosthenes, around about 200 BC, actually accurately measured the size of the Earth. Hipparchus, around about 100 BC, produced the first catalogue of the stars, derived the magnitude system which we still use today to classify the stars. But then Ptolemy, in the 2nd century AD, he postulated that we had a geocentric cosmology, that everything was going around the Earth. This led to concepts like epicycles and deferents, which I'm going to explain to you, complicated motions to try and explain what was seen in the sky. Unfortunately, Ptolemy's ideas proved to be wrong, proved to cause a stasis in human thinking which lasted for over 1,000 years until the birth of science in the Renaissance period. Let us tell the story. Let's start by one of these great successes of the ancient Greeks, Eratosthenes measuring the diameter of the Earth. He realized that at the solstice, the sun above a place called Syene in southern Egypt was directly overhead, whereas on the same day in Alexandria in northern Egypt it wasn't quite overhead. It was an angle of about 7 degrees to the vertical, about 1/50th therefore of a circle. He also measured the distance from Alexandria to Syene. It was 500 stades in the unit of the day. In modern units, it works out that the Earth's diameter is about 13,000 kilometers. That's very close to the actual modern measure of 12,756. Eratosthenes virtually was correct in his measurement of the diameter of the Earth. However, the geocentric view was what persisted and was left from the Greeks after Ptolemy's day. This view that everything was moving around the Earth. After all, we do appear to be stationary. It does look like the stars and the planets are all moving around the Earth. It is a natural view to take of the cosmology of the universe around us. However, it does lead to some rather artificial concept, as we're about to see. Essentially, the idea is that the Earth is imperfect, and outside the Earth, the stars, the planets are a perfect place. So everything has to move in a circle, because a circle is a perfect geometrical shape. Well, this leads to a problem. Let me explain the problem. It's trying to explain the motion of some of the planets like Mars. So Mars typically is moving towards the east with respect to the stars. It's moving in an orderly way towards the east. However, sometimes it appears to turn around and move back towards the west before turning back again and moving towards the east. We see this kind of S shape on this diagram over here. What is causing that? Well, Ptolemy's idea had to do with what he calls deferents and epicycles. In fact, Ptolemy wasn't the first person to postulate this. Even Hipparchus, a few hundred years before, had thought along similar ideas. Here's the idea. The planet is going around the Earth in a perfect circle. However, because it sometimes appears to go backwards, it needs a second circle on top of it. He called these two circles a deferent and an epicycle. So when you're on the top part, here of the epicycle, you're moving in the same direction as the deferent, you're moving in an easterly direction. But when you're on the bottom part of the epicycle, you're moving westward, you're going against the normal motion. So this was a qualitative explanation for what was going to go on. Unfortunately, it doesn't work if you want to be quantitative. You've actually got to have epicycles upon epicycles upon epicycles to make all sorts of corrections to try and explain what's really going on. There was a stasis in human thinking which lasted for over 1,000 years. It wasn't until the 1400s, early 1500s, that Nicholas Copernicus, a Polish astronomer, actually came up with a much more natural explanation for what was going on. He moved the center of the cosmos from being the Earth to the Sun, and he had all the planets traveling in perfect circles. They still were circles, perfect circles around the Sun. And now he could explain the retrograde motion seen here in this loop in the path of Mars by simply the Earth overtaking Mars in its orbit and Mars being seen against a distant backdrop of stars. This certainly provided a much more natural explanation. However, it still did not provide an exact fit. It took other scientists, as they became to be known, to explain that better. Kepler, in fact, came up with the first empirical laws of motion. He based them on measurements that his mentor Tycho Brahe made. He looked at the motions of the planets, and rather than traveling in circles, he realized, in fact, they were kind of traveling in like a kind of squash circle, what we call an ellipse, with the Sun at one of the focuses. He also had a law which explained how fast they moved. He realized that when they were close to the Sun, they moved much faster when they were further away. And he came up with a second law, which he based upon his data, that they travel equal areas in equal times. What that means is the time it takes to go from A to B is the same as it takes to go from C to D if these brown areas are the same area. So you're going much, much faster along this portion of the orbit than you are on this portion when you're further away from the Sun. However, the real revolution in human thinking actually came from the Italian astronomer Galileo Galilei, who used the telescope to look at the stars. He didn't invent the telescope, but he was the first person to look at the stars and record the observations they made, which started in 1610. Let us very quickly run through some of the observations Galileo made, which changed our perception of the universe around us. He looked at the moon, and rather than being a perfect sphere, he could clearly see craters, imperfections on the surface of the moon. He looked at Venus through his telescope, and he could see phases akin to what we see on the moon, except in this case, we see as we go from the different phases full to a thin crescent, the actual size, the angular size of Venus changes in the sky, quite different to the phases of the moon. He looked at the Sun, and the Sun, rather than being a perfect sphere, had these blemishes on them, sunspots, which also appeared to move across the surface of the Sun. But perhaps most dramatic of all was when he looked at Jupiter, and he saw these 4 spots around Jupiter, and they're all in a line. Moreover, when he observed from night to night, and here's a sketch from Galileo's notebook, here's Jupiter in the circle, and the asterisks are these spots, he saw they were moving. They were clearly in orbit around Jupiter. Here was another object in our solar system which was clearly the center of its own motion. The Earth could not be the center of everything because here was another object that was. So Galileo's observations really overthrew any thought of a geocentric universe, gave strong support to the heliocentric universe, but even more importantly, it got people thinking about what was happening in the sky, trying to understand the observations they were seeing. It was the birth of science. Thank you. That concludes the first of our Astrobytes, Armagh Astrobytes.